So I'm gonna share my slides. So can everybody see the slides?
Yep.
The transition of the slides is doing okay?
It looks like it.
Yeah, it's working.
Okay. Yeah. I don't know why the chat box doesn't pop up. So can anybody just type a message in the chat room? I didn't see anything in the chat room. Yeah, but anyway, if you want to ask a question, just feel free to ask. Sometimes there's no reminder about the chatting room. I'm making efforts to catch any question in the chatting room as well. But sometimes when I do the full screen sharing, it doesn't show up. Okay, I think okay. Right, it's good. It's still good for everybody, right? The transition of the slides.
Yeah.
Yeah.
Okay. So I think it's time for us to begin, right? So first of all, if you haven't um, started doing your homework one, please start right now. So we have well about like 1 week, a little bit longer than 1 week to finish homework one. I think even you start right now, it should be sufficient. But don't wait until like the last 2 days or last 1 day to do the homework. That won't be sufficient. Okay. And the second thing, I just want to remind everybody again, please start thinking about your project, competitive project in Kaggle, or exploratory project with your team member, or your solo explore project. That's fine. Right? Think about some research project you're interested in, and come and discuss with me or our TMs. Um, in the last I think Tuesday, a few students came to me and discussed their ideas. I think they're really cool, right? So if you want to do some exploratory project, please start to think about that. Think about now, and they want to do the Kaggle project, right? So the TM um, has shared with you the link. So click into that link and register account and fill out the Google spreadsheet so that our TMs can track your records in submitting the solutions to the Kaggle task. And remember, you have to at least submit two solutions. It's not necessary to be very good. It's just dummy submissions to ensure that um, uh, your setup the setup of your Kaggle computation task is right. Okay. Yeah. So let us talk about the course content, right? So in the last lecture, we introduced the we introduced the basic idea about computational learning theory, right? So again, don't worry, we're not gonna give a very in-depth discussion about computational learning theory. That was another class, actually. But we want everybody to understand the basic concepts, which are kind of like fundamental in machine learning, and how theoretical people think about uh, machine learning, right? How do we characterize the goodness or the badness of a learning algorithm, right? What kind of models and learning algorithm are viewed as good or bad, right? So you have saying that some kind of definition sounds a little weird, but they do have their own rationale, and we discussed in the last lecture, right? So to give a quick review, and based upon which we'll continue, right? So in the last lecture, we introduced a few notations like instance space consists of all possible instances we're going to predict with our learning algorithm. We denote it by X, output space denoted by Y, and a key assumption about our supervised learning is that we assume both the training data and test data are independently sampled from some unknown distribution over the instance space X. So in practice, in the most cases, in practice, you actually do not know what is D, right? But you can access it. You can draw sample from that. Um, and it's likely that D is so complicated you even don't have a closed form representation for the density or whatever. And then we assume that there is some kind of unknown target function which maps the instance from instance space to the labels in the output space. And this target function is taken from a concept class C. So concept class C defines the type of target function we want to learn from data, right? Um, like suppose we know that our target function is a second order polynomial, then your concept class will be all second order polynomials, right? If you know your function is just linear, then your concept class then your concept class is just all kinds of linear functions. So the concept class actually index the type of learning problem we want to solve, right? And those are about like target function, right? Of course, when we conduct learning, right? The learning is essentially a search procedure, and it is a training data guided search procedure, right? And the search must have a range, right? So what is a range? Range is called the hypothesis class or hypothesis space, big H, right? So the learning is essentially to pick up a hypothesis from the hypothesis space, which can best approximate the target function f. So we denote this learn hypothesis by this small h. So remember, it is still a mapping from the instance space to the output space. Right? And big S is used to denote the set of M training examples drawing from the data distribution D. Right? And the label of those training examples are given by the target function f. And then we introduce two fundamental concepts, right? It's very, very important. The first is called the true error or the generalization error for any hypothesis H. So the definition of true error is the probability that the prediction made by the hypothesis is different from the prediction made by the target function f. Because this is talking about like if you sample an arbitrary instance in an instance space. So it is under the unknown data distribution. That's why we call it probability, because the randomness comes from the test example. And h of x and f of x are both random variables. So we can say, okay, what is the probability? So the so this true error or the generalization error as someone um, raised the question in last lecture, right? So in practice, you will never be able to calculate the exact true error or the generalization error. So in practice, we always like um, randomly join like 1,000 test examples from the instance space and then do the prediction and calculate the test error, right? But those test error are all kind of statistical estimate of this true error. Conceptually, there is always a constant non-random true error which accurately measure the performance of your learned hypothesis. And this is important in computational learning theory because we always need some kind of golden standard and golden measurement uh, of the learning performance, right? And our all analysis and guarantees and conclusions are based on description of this true error in terms of other errors, right? And those are about true error, right? And in contrast to the true error, uh, the other commonly used error is called empirical error, right? Denoted by S because S is the training data. So empirical error is essentially the training error. You use the hypothesis H to predict the label of the training examples in the training set, right? And then you just calculate the error. This is empirical error. So our rationale or our assumption is that we want to achieve a smaller true error by minimizing the empirical error. So now I want to ask, what is the formal definition of overfitting? Yes, just to help you recall the concept we have discussed in the last lecture, right? So can anybody give me a hint?
Yeah, isn't it if our empirical error is much smaller than our true error, then essentially it's just it's overfit. It's predicting well for based on the model, but not in reality in general.
Yes, exactly, right? Perfect. So yeah, a formal definition of overfitting is just what you said, right? If we find that the empirical error is much smaller than the true error, meaning that your performance in predicting training data are far better than in predicting any future unseen examples. This violates our expectation that good empirical error will lead to good true error or the generalization error, right? That means some problem here, right? Perhaps there's some kind of noises corrupting the training data. So those you fit the noises so well and lead to bad hypothesis, which gives a larger true error, right? So this is a formal definition of the overfitting. And then we'll talk about under the context of computational learning theory, right? How should we define a good learner, a good learning algorithm, right? So we first analyzed, first discussed why we cannot expect a learner can exactly recover a concept, right? In some ideal cases, yes, it is, but in practice, in most real world applications, this is unrealistic. Why? Because of finite size of training data, right? So even to fit the training data, there could be multiple equally well target function in the concept space, right? So that means fundamentally, in this case, you're not able to recover the original concept. You're limited by the size of training data, right? And also some kind of agnostic. We recognize that actually on same examples, their labels are totally agnostic. Although we expect that they should be kind of closely related to the training set, but there's no guarantee on that. There are always some kind of like cautious belief under some uncertainty, which we'll discuss later, right? And 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 then we discuss what if we step back and just um, expect our learner can always give a close approximation to the target concept. And unfortunately, this is not feasible as well. I mean, in practice, for machine learning practice, right? The reason is that the learning performance is not only dependent on the particular model and algorithm you choose, but also depends on the training set, right? So remember, the training set are drawn from some unknown data distribution, right? So the quality of training set is kind of like random, right? In one collection of training set, they can well cover all kind of cases in the instance space. Well, probably by fitting this particular good quality training data to your learning algorithm, you end up very good approximation to the target concept, right? But what if in other case, right, you end up with a very bad quality training set? All the examples are concentrated on small corner in the instance space, right? Of course, your learned hypothesis won't be very good, right? So we need to consider. So by considering the randomness coming from the training data, right? So we can not always expect a learning algorithm, no matter how strong it is, um, can give you a close approximation um, uh, in every possible cases, right? So then what is a realistic expectation of a good learner? We need to consider some kind of probability, right? We need to introduce some probability statement. So basically, in general, we consider a good learner is that it can with high chance to learn a close approximation to a target concept. Like remember, imagine that, okay, you have a good learner, meaning that, okay, if I just random sample 100 collections of training set, and in 90% of chances or 90% of cases, the use these data sets can give you a very good approximation to the target concept, then we'll say, okay, this is good. Right? So based on this idea, right, this more realistic expectation, we introduced a key concept in the computational learning theory. It's called probably approximately correctness, right? So to define pack learning, we need to first quantify our expectation of good learner. So how to quantify it? We need to designate the small parameters epsilon, delta. So epsilon quantifies how close the learned hypothesis to the target concept, right? And delta quantifies how high the chance your learner can get such a good hypothesis, right? So if we use a more like accurate language to express our expectation for a good learner, it will be like this, right? It's a little bit weird, but we'll read it for 1,000 times, you'll get used to that. So with probability, at least 1 minus delta, a learner produces a hypothesis with error, true error, at most epsilon. Then we say, okay, this learner is good, right, in terms of epsilon delta setting. Of course, the smaller epsilon, smaller delta, meaning that your learning algorithm is better and even better and more efficient, right? So now we can define the pack learnability. So the pack learnability just measures how good a particular type of learning algorithm can learn a type of target functions. So we say the concept class C is pack learnable by a learning algorithm L with hypothesis big H if for every possible target function in this concept class, for every possible data distribution over the instance space, and for arbitrarily chosen epsilon delta, as long as L use a polynomial number of training examples in these four numbers, then L guarantees to return a good hypothesis with very high probability. And how good a hypothesis? The true error is at most epsilon, and how high the chance? The probability is at least 1 minus delta. So basically, the idea behind this lengthy definition is relatively straightforward. Although, to be rigorous, you have to give a long and paragraph to introduce this idea, right? So we can further define the efficient pack learnable, meaning that L not only uses a polynomial number of training examples to well learn this hypothesis, right? Well learn this target function, well learn every target function in a concept class, but also the execution of this learning algorithm is efficient as well. And is also, the time complexity is also polynomial to these four numbers, 1 over epsilon, 1 over delta, n is the dimension of your feature vectors, right? Dimension of which is essentially dimension of your instance space and the size of hypothesis space H. So what kind of insights does pack learnability imply, right? So from the definition of the pack learnability, we actually impose two requirements. The first is the polynomial sample complexity, meaning that if we can claim that a learning algorithm pack can efficiently learn type of target functions, then that means, okay, we do not need too many examples. We only need a polynomial number of examples to the parameters which describe this family of tasks, right? And also, we require polynomial time complexity. That is related to that defines how efficient the execution of your learning algorithm. So, so you can see that the pack learnability is essentially a very strong definition, very strong requirement. It is kind of worst case definition because the algorithm which satisfies the pack learnability must meet its accuracy commitment for every possible data distribution. So the distribution is free. And for every target function in the class C, right? So someone asked if it is too restrictive, right? The bar is too high, right? Do we have a other definition? Yeah, of course. Based upon the pack learnability, people have proposed a variety of relaxations, variants to describe to differentiate different types of learning algorithm under different contexts, which we're not gonna discuss in detail in this class. But just to let you know, perhaps this is a most naive definition and most fundamental definition. Okay, so far we just gave a quick review about all those theoretical terms and concepts we discussed in the last lecture to ensure everybody is on the same page, to ensure everybody feels comfortable. Is any questions so far? Everyone is good, right? Okay, I assume everyone is good. Okay, so now we want to use this relatively rough framework and just a few terms we have discussed so far to mathematically justify the Occam's razor principle. So, so what is the principle of Occam's razor? Any hint?
Isn't it that if there are like several methods for coming to the same conclusion, we want to pick the one that's the simplest?
Yes, exactly, right. So we just give a kind of like a qualitative description about the principle of Occam's razor, right? When we introduced the ID3 algorithm, decision tree learning algorithm, right? So we know that for the same set of data, we can have like multiple decision trees. Each of those trees can equally well represent the whole data, right? Then there comes a selection problem, right? Among all those consistent trees with the same data, right? Which one should we rank as the best, right? At that point, we just cite this principle of Occam's razor and claim that we should choose the smallest tree. Okay? And in general, this is kind of like widely used philosophy, scientific engineering principle, meaning that for any theory or any phenomenon, for any data, right? And suppose you have a bunch of models or theories which can equally well explain the data or the phenomenon, and we'll always prefer simpler models, simpler explanations with least assumptions, with least model size, with least model parameters, whatever. So if we can summarize the principle in one sentence, it's just that it is like this, right? Never posit plurality without necessity. Right? So this was first proposed by William of Occam, right? But this is not talking about like science or engineering, just talking about like schools of philosophy, right? Because you might have like different philosophies to explain some general things, right? And he just gives us a guidance, right? How do we choose? How do we favor those different philosophies, right? And now we want to use the computational learning framework to give some kind of justification of Occam's razor, meaning that we'll show that if we follow the Occam's razor principle, it can give us some benefit. So now let us, to formalize this Occam's razor, right? And let us look at a claim. So the claim is under some kind of consistent learner, like in theory. We assume that we have some kind of consistent learner. We have a large enough hypothesis space such that in any cases, our learner can always find a hypothesis which can perfectly fit the training set, meaning that your training error or empirical error is always zero, right? So underlying this setting, we now give a claim. The probability that there is a hypothesis, small h, that is first consistent with all M training examples. Second, the generalization error is bigger than some epsilon. This probability is upper bounded by this guy. The size of h, the size of big H times 1 minus epsilon to the power of M. So what does this mean, right? This actually defines an event, right? As some kind of event where we're unwilling to say, meaning that we have some good hypothesis, right? We have found some good hypothesis, which can, which is consistent with all the training examples, but the true error is big, meaning that it does not generalize well. Consistently, yet bad, right? So we do not want this to happen, right? So we want to know what is the upper bound of this bad event to happen. What is the upper bound of the chance for this bad event to happen, right? So now we can give this bound, which is essentially a pretty loose bound. So we know that we can prove that the chance of this bad event to happen is less than or equal to the size of a whole hypothesis space times 1 minus epsilon to the power of M. Like epsilon actually indicates the tolerance of your generalization error, right? So if your learned hypothesis whose true error is bigger than its tolerance, is meaning that okay, it does not generalize well, right? It beyond my tolerance. Does this claim sound understandable? Like, is everybody good with this claim? Any questions so far? So assume everybody is good with that, right? This is just a claim, right? And we need to prove that claim. Okay. So how to prove this, right? So we can take a look at a particular hypothesis H, right? And this H, we know it is bad. It is bad, meaning that its true error is bigger than our tolerance level, epsilon. And I want to see how likely it is still consistent with all M training examples. How can show that, right? Now, we should use what we have done in homework 0, right? Where we reviewed our probability knowledge, right? So because the true error of H is, we know, is bigger than epsilon, that means the probability H is consistent with one training example will be less than 1 minus epsilon. Why? Because according to the definition of the true error is a probability that your prediction of H, right, disagrees with the ground truth, right? If it is bigger than epsilon, that, of course, the chance it agrees is less than 1 minus epsilon. So we got our first observation because H is bad hypothesis, and then the chance that it can correctly predict one particular training example will be less than 1 minus epsilon, right? And further, because our training set contains M examples, which are independently drawn from the unknown data distribution D, and so it is easy to derive that the chance that H is consistent with all M examples will be less than 1 minus epsilon to the power of M, right? Because all those examples are independent, meaning that each event H is bad that consists of one particular example are independent, right? So H is bad but consistent with all M examples. The chance of that is equal to the product of the probability of each individual event, right? With each individual event, its chance is upper bounded by F1 minus epsilon. So their product is upper bounded by 1 minus epsilon to the power of M, right? And now, so far, we know that as long as we have some specific a particular bad hypothesis whose true error is bigger than epsilon, we know that it still has a tiny chance to be consistent with all M training examples, right? So this chance is upper bounded by 1 minus epsilon, right? But it's still, but what we observe so far is different from the claim, right? The claim says that what is the probability that there exists some bad hypothesis rather than for some particular hypothesis. Right? So we want to know there exists some bad hypothesis, and this bad hypothesis is consistent with all M training examples. Right? Now, how can we derive this probability, right, based on our observation? So now we need to look at how we decompose events. Right? So actually, the event we care about is there exists some bad hypothesis in the hypothesis space that is consistent with M training examples, right? So the previous observation is based on some more atomic event that a particular hypothesis H is bad, but consistent with M examples. Now, we want to build up a relationship between this small event and this event A that we're really interested in. Right? How can we construct even A in terms of this. Any idea? Any thoughts? Or any guess? Okay, so okay, yeah. Let us just look at how we construct atomic simpler even, right? So actually, we can redescribe the even A in another way, meaning that exist some bad hypothesis consistent, some bad hypothesis in hypothesis space, but consistent with training examples, meaning that either, not either, right? Meaning that the first hypothesis in big H is bad or consistent, but consistent with M examples, or the second hypothesis in the space is bad, yet consistent with M examples, or the third hypothesis in big H is bad, yet consistent with M train examples, or a bunch of atomic events until the last hypothesis in the hypothesis space H is bad, yet consistent with M train examples, right? This is how we express existing, right? The even about the existence even, right? So now we can define each of those atomic event, denote them by like B1, B2, B3 to B big H. Right? So now we decompose the even A, which we really care about, as a union of a set of atomic events B1, B2, B3 onto B big H, right? So each like BK is actually saying, okay, HK, the case hypothesis in hypothesis space, is bad, meaning the true error is less than epsilon, but it is consistent with all M train examples. So actually, A is a union of this size of H atomic events. You enumerate every hypothesis in hypothesis space. So any questions so far? Is everybody good? Oh, this is too easy. Okay, assume everybody is comfortable, right? Everybody is on the same page, because this is really important for us to show this claim, why this claim is right. So now, just use the conclusion what I'm showing. You are required to prove in homework 0, right? So we know that the probability of the even A will be upper bounded by the summation of those individual events, right? P of B1 plus P of B2 plus P of B3 until P of B like size of H, right? Because this is union, right? The probability of union of set of events is less than or equal to the summation of the probability of each events in the union. Right? And then each probability here, right, on the right-hand side, is upper bounded by 1 minus epsilon to the power of m, right? This is our previous assumption, right? And our previous observation, right? the previous observation tells us that for a particular hypothesis, if it is bad but consistent with m examples, this chance is upper bounded by 1 minus epsilon to the power of m. So now we have a like size of hypothesis h upper bounds. We add them together, we'll end up with our final bound, upper bound for the probability probability of even a, right? So basically, we said the probability of even a is less than or equal to the size of hypothesis h times 1 minus epsilon to the power of m. So a defines exactly this bad even, right? Meaning that we have some hypotheses which can perfectly fit the training data, but the true error is bigger than our designated tolerance level. Any questions so far?
I had a question that also from Mario in the chat. So for it to be consistent, does that mean if the error is less than the number of hypotheses times 1 minus e to the m, does that mean it's consistent, or is
No, consistent means that the training error is 0.
oh
Yeah, it's error s h is 0, meaning if you use your hypothesis h to predict all the m examples here, then the error is 0. But obviously, it's different from the generalization error, right?
I'm a little confused on that. So what's the difference between the generalized error d versus our consistent error that's 0?
Oh, this is a wait a second. I'm trying to find out the chat. Does anybody send a message in the chat room? Because right now I didn't see any chat message box pop up.
Yeah, there's some Zoom chats, but
That's weird. I think just give me 1 second. Oh yeah, it's pop-ups. Okay, so consistent with m examples just means the training error is 0 or the empirical error is 0. It relates to the empirical error we just defined in the computation learning theory, right? So when we say h, when we say h is consistent with m examples, it just means the prediction of h on these m examples are exactly the same as the ground truth, meaning that your empirical error is simply 0. Does it make sense? But this empirical error is totally different from the true error or the generalization error. Remember, the generalization error is defined as the probability for arbitrary example sample from instance space. The prediction made by h is different from the prediction made by the by the target function.
okay, that makes sense. So like empirical error is based on training data, and then generalization error is based on could be any
Yes.
data.
Yes.
Okay.
So basically, it's okay, if I want to quantify, I want to upper bound the chance that you have a 0 training error, but you have a relatively large generalization error. Does it make sense? Any other question? Yeah, I think I would like to read out a few messages in the chat. This give very good description. It basically means how likely we match our training data too well, but it won't generalize to test data. Okay, Okay, so now let us continue.
Sorry, one quick question. If you go back to that last slide. So when we're saying the reason we're taking a case where H is bad is simply we're just going worst case scenario in this proof. We're saying that H is a bad target function estimate. And so we're basing this proof off the fact that even in the worst scenario, this inequality still holds true. Is that like the idea behind it?
I think it shouldn't say even. It should say, okay, what if the in the worst scenario, what's the chance of this worst case or worst scenario will show up? Yeah.
Okay. Cool.
Okay. Any other question regarding the understanding of this?
So the hypothesis, the size of the hypothesis here means that the total number of hypotheses that is present in the hypothesis space.
Yes, exactly.
But that can be a very large number, right? Like it can be infinity as well. If we just take an example of 2D space, that might have infinite hypothesis for a training data set.
Yeah, you're right. I think you point out you mentioned very good point. Yeah, this is some deficiency because this is like simple analysis, and we'll see that when big H is infinite, right? It consists of infinite possible hypothesis space. Then all those analysis is not meaningful at all, right? And later we'll address this problem. We'll derive another sample complexity bound. But right now, just assume your hypothesis space is finite. You can count how many hypotheses in total your hypothesis space. And of course, when H is very large, this is a very loose bound, right? Okay, so everybody's comfortable right now, right? So basically, we have a showing that what is the largest chance that we find a hypothesis which has zero training error, but with a large true error or the generalization error. We can bound this probability. This is definitely something we do not want, right? But there is always the chance for some bad event happen, right? We just bound the probability that this bad event happens, right? So it is bounded by size of hypothesis space H times 1 minus epsilon to the power of m. Right? So obviously we don't want that, right? We don't want this event to happen. We want to control, want to manage this the chance that this event happen, right? How can we do that? Right? How can we decrease the probability this event to happen? Any idea? Is there any method that pop up in your mind can be used to prevent such event happen? Meaning, prevent that we find a good hypothesis in fitting training data, but bad in the generalization performance.
Wouldn't that be all the strategies we've talked about for reducing overfit, and like pruning and stuff like that?
Oh no, right now we didn't talk about overfitting. Well, you can see it's overfitting, but we're not talking about the reason for the overfitting. So in the previous case, we said okay, overfitting is caused by some noises, some incorrectness in the training data, right? But right now we don't assume there are any noises, corrupted the training data, making inconsistent match between the training and test examples. We don't have any. We do not assume this. Right? Right now we assume okay, the training and test sets are all good. They're all sampled from the same data distribution. There are no extra noises, right? But we still have the chance that you learn a hypothesis which perfectly fit the training data, but perform badly on the future on seeing examples, although this chance is relatively low, but we still need to analyze them.
Gotcha. So then can we just say like the way to reduce this chance is to have more training data?
Yes,
Or
exactly.
is that already accounted for?
Very good. Yeah, exactly. So this fits our intuition, right? So and if you look at this bound, you can find the rationale as well, right? If we increase number of training examples, but hypothesis space, remember, is fixed, right? So increase m, you're actually multiplying with a smaller a constant less than 1, right? So if you keep increasing number of examples, this bound is decreasing, right? Decreasing very fast. Decreasing very fast. But intuitively, you can imagine that if we add a lot of like training examples, those training examples kind of like uniformly cover the whole training instance, then we're much less likely to perform badly on seeing examples because they're all like covered or surrounded by the training examples. So now we want to give some kind of like quantitative analysis. Suppose I want to control the chance of this bad event to happen to be under some level, say delta, right? Delta is my another tolerance level, right? I do not want this bad thing to happen. I do not want the chance of this bad event to happen to be bigger than epsilon. Right? I want the chance to be strictly smaller than epsilon. Right? Then how many training examples would we need to ensure the chance is smaller than the level, the tolerance level? So how can we achieve that? Because we know the upper bound of this bad event to happen is this, right? So as long as we can ensure this upper bound is less than our tolerance level, then we can ensure, okay, the real chance of this event to happen is less than delta, right?
A quick question: where's epsilon coming from again, or is that just a number we're putting in there?
The epsilon is the tolerance level for the true error. It depends on your problem, right? So for problem 1, you might will like epsilon equals to 0.1. If your true error is bigger than 0.1, you will, okay, you're performing badly, right? And for another problem, you might designate epsilon 0.05, right? Meaning that, okay, if your learned hypothesis has true error bigger than 0.05, then we'll say, okay, this hypothesis is bad. So basically, epsilon just defines when this hypothesis is bad.
Gotcha. It's like when we consider it to be like not sufficient for our needs, or
yes, exactly. Not sufficient for our needs, not sufficient for our application, whatever.
Interesting. So like it's a little confusing because we have epsilon and now we're introducing, another tolerance factor, right? It seems like we would only want one tolerance factor. We want, say, like we want our endpoint to be this accurate, right? Just there's a probability. I'm struggling to conceptualize how we parse like that into these two different.
So these two different tolerance levels represent our represent our different tolerances. So different tolerances. The one tolerance is about the goodness about your learning performance, which can satisfy your need, right? It's about the generalization error. And another tolerance, delta, is about the chance that this event to happen. So remember, in whatever situation, you're always gonna have a bad thing, that you have a consistent hypothesis, but your true error doesn't satisfy your need. We want this chance to be smaller than some designated tolerance level, which is expressed as delta.
Okay, so could you say it like epsilon is how accurate we want our model or our training, our machine learning algorithm to be, And then delta is how low we want the chance of it learning improperly to be.
Yes. Yes.
Right.
Exactly.
So for every time we try to learn stuff, this is the probability that like it'll learn it wrong, kind of a thing.
Yes. Yes.
Ooh, all right.
Yeah. This is just you view the problem in different aspects, right? Is I want the learning performance to satisfy this. This pretend to our particular problem. But also we want during the learning procedure, I want the chance that it learns improperly to be enough small, right? So it's different. It's actually different things. So any other question regarding this? Okay. So now I want to control. I want to control the probability that our learning behavior is our learn improper hypothesis to be smaller than the delta, right? So to achieve that, we just want to ensure the upper bound of this chance to be smaller than the tolerance level, right? So then we only need to solve the inequality here, right? So the left-hand side is upper bound of this probability of the bad event, right? Bad learning event. And the right-hand side is the tolerance level, right? We just need to solve this inequality in terms of the number of training examples, right? According to our analysis a minute ago, right? We know when we increase number of training examples, this chance has become much smaller, right? So to solve this inequality, you can just take a logarithm of both sides, right? And to facilitate analysis, right? Not to like give a really tight bound. We just want to show something, right? So we can use another bound, right? And this comes from the Taylor expansion of the e to the minus x, right? We know that e to the minus x is bigger than 1 minus x. So we can construct another bound about the left-hand side, because logarithm of 1 minus epsilon is less than minus epsilon, right, from here. And then we can construct upper bound of the right-hand side. Right? Then we want to make this upper bound to be less than logarithm delta. In that way, this inequality, this original inequality will hold for sure, right? So if you write it out, it's just like that, right? So I construct a upper bound of the left-hand side here, and I want to solve the inequality that this upper bound also is less than logarithm of delta. And then when we solve this, of course, when this holds and this holds as well, right? And then when we solve this, it's very convenient. And simply arranging the terms, we derive that m epsilon is bigger than this, and divide both sides by epsilon. You end up with a lower bound of the number of training examples, right? So that is, if the number of training examples is bigger than this guy, then the probability of getting a consistent but bad hypothesis is small. Smaller than the designated tolerance level delta. So if I connect back to the whole definition here, right? What you can see is that if a kind of like integral description conclusion is that if the number of training examples m is bigger than this guy, then we claim that the probability we find a consistent hypothesis with m training examples, but has true error bigger than epsilon, is less than delta. More succinctly, right? We can say, okay, as long as m is bigger than this lower bound, right? As long as the training examples are more than this lower bound, then the chance that you get a consistent yet bad hypothesis will be less than delta. Right? And on the other side, right, okay, we can equivalently restate this conclusion by as long as m is bigger than this lower bound, then with high chance, 1 minus delta, right? You have a consistent hypothesis whose true error is less than epsilon. Right? It's just another way to state the same conclusion, right? Then we'll end up with our final conclusion here, right? So let big H be any hypothesis space, and then if we can use a number of training examples M, which is bigger than this guy, then with high chance, which is at least 1 minus delta, a hypothesis which is consistent with the training set of all M examples will have the true error less than epsilon. Does it make sense? So the language is kind of twisted, but the idea is like that. The idea is here. So idea is relatively straightforward. So basically means, okay, if you have enough number of training examples, then a consistent hypothesis with all the training examples have a high chance to have a small generalization error. And that's all the result we have derived so far. Let me repeat again, right? As long as the number of training examples is enough large, right? Larger than this lower bound, then your consistent hypothesis will have the true error also very small with high chance. How small is it? Less than epsilon. And how high the chance? The probability will be at least 1 minus delta. So of course, the lower bound of this number of training examples is determined by the designated error level and the designated confidence level, right? Delta and epsilon. Any questions so far?
Yeah, back on the delta and epsilon thing, I get like what the symbols mean, but I'm not sure in how it's represented exactly. So like, I'm sure both of them are probabilities, they're fractions, right? Or like, you know, so delta is the probability that, what exactly?
Delta is the probability. No, actually, you should see it. 1 minus delta is the probability that your learned consistent hypothesis is performing well.
Okay, so 1 minus delta is that it's performing well. So delta is that it's performing poorly, essentially.
Yes, exactly.
Okay. And epsilon is the probability that it errors, right? That like it predicts.
Epsilon is not probability. Epsilon is the level of the error.
Oh, like how often will it, right?
Yes. Yes.
Error. Okay.
Yeah. Epsilon indicates how well your learned hypothesis performs in testing the future unseen examples.
Got it. Okay, so that's nice that they're both measuring error in some way, right? They're measuring the thing we don't want, basically.
Yes. Yes, exactly. So epsilon indicates, okay, if you think your learned hypothesis is satisfactory, then what is the threshold? Right? What is threshold of about the accuracy your learned hypothesis in predicting arbitrary test examples? And delta just means how likely your learned hypothesis performs badly or performs poorly. And according to our intuition, right, we know that when we increase the number of training examples, we're gonna lower the chance that our learned hypothesis performs badly, right? And now we derive a kind of quantitative lower bound of the training examples, right? And as long as the number of training examples is bigger than this lower bound, then we guarantee our learned consistent hypothesis will have a high chance to perform well, right? Regarding that, but how do we quantify the high chance? We say it is at least 1 minus delta, right? And how do we quantify performing well? I mean, is generalization error is less epsilon. So is everybody good? Yeah, I mean, if you still feel a little bit confused, uncomfortable, don't worry. Just after class, read through this definition once again, or twice, or 3 times. You'll get used to that. So the idea is the idea is there. Right? It's just saying, okay. So first, it says, okay, no matter in what cases, right? Even you find a hypothesis which perfectly predict all the training examples, there's still a chance it performs badly in the future on same examples, right? And what we did is just to upper bound the chance. And then we want to develop a strategy to control the chance. What is the strategy? We need to increase the number of training examples, right? And then we further derive a quantifiable bound, right? We derive a lower bound, and we show that as long as the number of training examples is bigger than its lower bound, then for any designated level delta and epsilon, and we can guarantee our learned hypothesis will have at least 1 minus delta's chance to perform well, or in other words, our chance of performing badly is no bigger than this designated delta. Okay, so now we want to look at what does this lower bound reflect, right? What does this guy right, on the right-hand side reflect? Right? So we find that the sample complexity lower bound is determined by a few factors. Right? First, it is proportional to 1 over epsilon. It means that if we want to expect our learner to have a smaller true error, then this lower bound will get increased, right? Meaning that you need more training examples. This is very reasonable, right? You want more accuracy in predicting future examples. You need to train a model with more examples. We need more training data. And the second observation is that we found that this sample complexity bound is proportional to logarithm of the size of hypothesis H. So what does it mean? It means that if we have a larger hypothesis, we have a larger hypothesis space, then to achieve the same error level with the same high chance, we need to use more training examples, right? So the larger, if we fix epsilon delta here, right? And consider you have a bunch of learning algorithm. Each algorithm uses a different hypothesis H, right? And then the larger the hypothesis space your algorithm uses, the larger the lower bound of sample complexity, right? Meaning that you need to use more training examples to ensure that your consistent hypothesis to have the same high chance to achieve the same true error, right? And finally, it is also related to 1 minus delta, right? Remember, delta indicates the confidence, right? That is the chance that you the chance your consistent learner, the consistent hypothesis performs badly, right? So if we want a higher confidence, meaning that we want a high chance that your learned hypothesis performs well, meaning delta is smaller, then the whole lower bound will increase, right? Meaning that you need more training examples. This is reasonable as well, because the more confident if you want to be more confident about the performance of your learned hypothesis, of course you need to fit more training data. Right? So now I want to ask, among the three terms which determine the sample complexity lower bound, which one reflects the Occam's razor's principle?
Second one.
Why?
Because hypothesis space can be as large as possible. If we expect it to be small, like we fix it to smaller number, we'll need less number of trainings sample.
Yes, exactly, right. So that's where we can see why Occam's razor is useful, right? So from the second term, we can see that as we just discussed, right? So suppose we have a set of we have several learning algorithms, each uses a different hypothesis space, right? And then we designate as the same epsilon delta, right? Meaning that we want each algorithm to find a hypothesis which has the same high chance to achieve the same true error level, right? And then we know that the larger the hypothesis space the algorithm uses, the larger the lower bound of the sample complexity, right? Meaning that you need to use more training examples. So if we follow Occam's razor, we should choose the algorithm that uses the smallest hypothesis space, right? The benefit is that we need less number of training examples. We lower the sample complexity. This is important in machine learning because in many applications, collecting the training examples is very costly. Right? The smaller number of training examples, the better. Right? So now we can see how we can justify Occam's razor, right? So from this simple lower bound on the is very ideal case, right? The analysis shows that Occam's razor actually favors smaller hypothesis space, right? Given that all the hypothesis space can provide you a consistent hypothesis. So any questions so far? So hopefully everybody, through this case, this case can deepen your understanding about Occam's razor and connects this relatively like qualitative principle to more rigorous mathematical justification, right? So now based upon those conclusions, right, we can come out a kind of mind, kind of like ideal algorithm in our mind to perform pack learning, right? If you want to examine if our learning algorithm, if some particular learning algorithm can pack learn family or a type of target function, how can you do that, right? So we just go through every function in every target function in the concept class, right? And then we just collect a sample of m examples, right? And when can we claim that h, the learned hypothesis, are close enough to f? We can just look at what kind of lower bound were m satisfied, right? If we can construct lower bound showing some epsilon delta, and then we can claim that under the probability with at least 1 minus delta, your true error is less than epsilon, because these are all derived by our previous theorems, right, and claim. So we can just increase number of training examples, and then look at when m exceeds this lower bound. Once m exceeds the lower bound, we can claim, okay, our consistent learner has found a hypothesis which is close enough to the target function f. And next, we're going to check whether M is enough large or is too large or not, right? So we just look at if M is polynomial in the relevant parameters. Remember, the definition in pack learning requires the number of training examples is polynomial in like 1 minus epsilon, 1 over epsilon, 1 over delta, dimension of the instance space, and also size of hypothesis space, right? Obviously, if M is bigger than this, that is fine, right? And in this way, we can verify if the consistent learner can effectively learn a particular target function in a concept class, right? And if we just enumerate and test the learnability for every target function in a concept class, then we can claim, okay, our learning algorithm can pack learn this concept class. And also, if you want to further demonstrate that it is efficiently pack learnable, then you need to ensure that your consistent learner, the running of your consistent learner, is not too too slow, right? It is the time complexity is also polynomial to the four numbers. So this is just to give you kind of like mind experiments, mind understanding that how do I check if a particular learning algorithm can pack learn a family of target functions. Okay. But as someone has pointed out, right, a few minutes ago, right, so far all of our analysis assumes that the size of hypothesis space is finite, right? If the size of hypothesis space is infinite, then this lower bound is meaningless at all, right? That means, okay, if you want to achieve a particular level of the true error with a particular high chance, right? And you have to involve an infinite number of the training examples. Obviously, this is infeasible, right? This is not meaningful at all, right? And under that, and in practice, there are many type of learning algorithm which use an infinite hypothesis space. This means that we need to develop new theory, new sample complexity bound, right? And we have to use other measurement to measure the complexity of a hypothesis space, which we'll discuss later. This is called the VC dimension. We'll introduce the concept of VC dimension later before we introduce the support vector machines. Okay, any questions so far?
I had a question about the hypothesis space. How is that computed generally? Like if we look at the decision trees that we're computing for homework 1, for example, like in the first problem, I think there's like 4 attributes and each of them is binary. So is it like a 4 to the 2 type hypothesis space?
Well, if you talk about a particular case, right, like decision tree, I think that is doable, and that the number of all type of decision trees is computable. Right? You can just calculate the combination of the splits, the order of the nodes in the split, and the branches and all kinds of stuffs. But I don't think you can simply calculate the combination of 4 over 2. You can get that. You should enumerate all possible cases. But it's finite. I agree. But in many other cases, the hypothesis space is not finite. It's infinite. Like a very simple model like linear regression, because all the model parameters are continuous, right? So a set of continuous parameters determine a specific instance of the model. Then you have infinite possible choices of those model parameters, right?
Right. Yeah.
And in that case, we won't be able to use logarithm size of hypothesis space because it's infinite, right? So we'll use another dimension, measurement is called the VC dimension. The definition of VC dimension is very smart. is actually very smart. And we can use that to measure the complexity of hypothesis space in many learning algorithms like linear regression, like deep neural nets, even like KN classifiers, which we'll discuss later.
Cool, thanks.
Thanks. So let's stop here, and we're gonna meet next Tuesday. So please do not forget to start doing your homework one, and consider your project. Okay, see you.
Thank you.
Thanks.